So everything I talk about is joint work with Martin de Hoop and Gunther Ullmann, or almost everything, I should say. It's going to be a preliminary theorem. So the basic problem that I talk about is determining the structure of an object, which could be big or small. And one way of doing it without breaking it apart, I mean, maybe it's big and you can't, or maybe it's small and you value it. Anyway, and so one way of doing it is sending waves through through this object, and then the question is, can we determine what's inside from this information? And the simplest thing you can get out of waves is their travel times, how long it took for a wave. So the wave is going in at some point and can come in and measure it at some other point, how long it took to get through. So an example would be seismic waves. You know, there are earthquakes somewhere near the surface of the Earth. And then you measure the seismic waves, and the easiest thing to do is to measure the travel times. I mean, the simplest thing to do. Okay, so so what I talk about today is anisotropic elasticity. So I give a bit more of an introduction to this, but let me just summarize things in case things get, I don't know, too, I just phrase things the wrong way. So anyway, the basic upshot will be that there will be different kind of waves, elastic waves in this case. So going to be these QSH waves, and their travel time. So they are going to be the nicest waves from the perspective of analysis. And their travel times will determine the axis of isotropy. So this is an elasticity versus a special axis that can keep varying from point to point, as well as some of the elastic material parameters. And then there's some other kind of waves. This is QP and QS waves, whose travel times conditionally, so under extra conditions, determine a subset of the remaining parameters in the sense of if some of the remaining parameters known, the rest can be recovered, or if there's a functional relationship between them. So one, so say others are a function of one, then they can all be determined. And there are issues why there's this conditional here, and there's a precise description, and I will say something about this. You already heard something about this in my grad student Joey Zhu's very quick talk yesterday. So this is sort of really a precursor to maybe where he started. All right. So and then one application is, as I already said, is in seismography, where definitely there's anisotropy in elasticity. So I mean, on a small scale, anisotropy is of course simple because crystals are anisotropic, for example. But even on a large scale, there is anisotropy, as discussed in various people. So Martin is the expert. I mean, relative to me, Martin for sure is the expert in these things. So I defer to him if there are any questions about that particular part of the applicability. In any case, so the upshot is, for now, that the symmetry axis symmetry axis can be recovered with our methods, but the full recovered elastic parameters require some extra relationships. And so often these are sort of well motivated by models, but for me it's going to be sort of black box. All right, and what we do to do this is to work in the setting of Riemannian geometry, which is really nice because it enables very clean and conceptual statements. So, I mean, the nice thing is that you don't have very complicated formulae in most places. But anyway, so what I'm going to start with is to recall a background result on which actually the strongest but easiest part of what I talk about relies. So, I mean, it's easy given this result. So this result is the following. So this is about Riemannian manifolds, which you can just think about them as say, a domain with boundaries, say, in Euclidean space. That would be a good example. But instead of having the standard metric, standard inner product of like what is the dot product of two vectors, it varies from point to point. Okay, and then you have geodesics in this world as well. And then you can ask, what is the distance between 2 points on 2 points on the boundary of this domain? So in the easiest situations, this just really take a there might be a unique geodesic connecting them, and it's just the length of that geodesic. And there's an upgraded version of this when the geometry is more complicated, and that's called the lens relation. So I'm going to sort of ignore this sort of distinction in most of this talk. So roughly speaking, what you are thinking about is the the travel time, just how long the geodesics are connecting boundary points. So this is what you would measure. I mean, if you think about if seismic waves were just described by the Riemannian metric, this is exactly what the travel times would measure. Okay, and then so the theorem just from 2 years ago with Plyman Stefanov and Gunther Ullmann is that in 3 dimensions or higher, under some convexity assumptions, which I illustrate in the next picture, so next slide, so it's probably easiest to just show that. If you have the same travel times, so it says length relations here, anyway, same travel times, then the 2 metrics are the same. So in what sense? So this is Riemannian geometry, and geometry is invariant, right? So you can use whatever coordinates you want, and you get the same thing. So what this means is that there's no way of that you can really, just from knowing the length of geodesics connecting points on the boundary, there's no way of figuring out what the actual metric is, whose geodesics give you this distance function. You can at most figure this out up to change of coordinates. You could reparameterize the interior of your domain. That's a change of coordinates. And so that's a diffeomorphism. And so up to such changes of coordinates, you can recover the metric. I mean, I'm saying recover here. I should be to be fair. Recover can mean a lot of different things. So here it's a uniqueness statement. So if you have 2 different metrics, a priori different metrics, that give you the same distance functions, they are the same in the sense that they are same up to a change of coordinates. There will be a stronger statement, which would be a stability statement, and there will be an even better statement, which is a reconstruction algorithm. So we haven't done this, but what this relies on is earlier work with Gunther Ullmann that I will hopefully get to towards the end. And that, in fact, is completely constructive. And there have been implementations or attempts at implementation. So, for example, by Gunther and the collaborator Eric Chung, there's a PhD student at Stanford in computational mathematical engineering who is also interested in implementing this. So, in principle, and in principle is not like a remote principle. It's almost reality kind of principle. This should be implementable eventually. All right. So in any case, the upshot is that under some assumptions, which I'll discuss in a moment, if you know the travel times of waves for waves that are given by geodesics of a metric, you can actually recover the metric up to what you can't do anything about, namely the coordinate invariance of the problem. It's not just that you can't do anything about. That's the whole beauty of it. So you really don't want to do anything about it. Anyway, so here's the picture of this convexity. So the way I state the theorem, it really corresponds to what's on the left-hand side. So remember, dimension is supposed to be at least 3, but I'm really bad at drawing pictures. So this is a 2-dimensional picture, but you should think of this as a ball in Euclidean space. And so maybe you're perturbing the Euclidean metric a little bit, and you're trying to figure out what is this perturbation for the purposes of this picture. And what you using as this function, which is convex, are these paraboloids. So their level sets are strictly convex or concave, whichever way you're looking at it. And I'll discuss in a bit, how this plays a role a little bit later. But basically, what this does, it helps you localize the problem. So it gives you a way of doing essentially what amounts to layer stripping, which the use of this, the way this will be useful is that there have been analytic procedures, an analysis procedure that's doing an appropriate inversion, and having small steps in these layers is what gives you small errors. Okay, so I will hopefully get to that. So that's this localization that's mentioned in the very bottom. The picture on the right-hand side is, of course, a very classical picture. So that's spheres, and that goes back to so mathematics and geosciences to Herglotz, Wiechert, and Zöpritz in like 1905 or something like that. If you have a spherically symmetric, medium, can you find the speed of waves from travel times? And in fact, so they have a condition, and that condition is exactly the convexity of these spheres. So relative to the relevant thing, which is the metric, that Riemannian metric that corresponds to this travel speed. So in fact, our condition is somehow the 100-plus-year-old condition, generalized. All right. So okay, so that was the geometric motivation. So the geometric background. So geometric background is that for waves that are given by Riemannian geometry, so they travel along geodesics, their travel times determine the metric, well, modulo some assumptions, up to the natural invariance of the problem. Okay, so we're going to be back to now elasticity. So elasticity is more complicated than Riemannian geometry in some sense, as we'll see. So the way I set it up, so I set it, I make it geometric. So the way we start is that we have a background metric. So this could be Euclidean metric. So we know so we love the Euclidean metric. It's nice and simple. And then so that's an inner product that tells you the inner product of vectors. And then we have a dual metric that's simply the inverse that tells you the dot product of covectors. In any case, elasticity is or anisotropic elasticity is described by a system of partial differential operators. So you have a matrix with so jk entry, I'm calling A jk, xv, so D is the differentiation. And so what you do, so it's going to be a little bit of PDE statement right now. So what you do when you have a PDE, well, the thing that matters most is the highest derivative, right? And so that's what gives rise to this notion called the principal symbol, which is super simple in this sort of situation. You're really just replacing the derivatives by the corresponding Fourier multiplier. So if I had Fourier variable, dual variable, so if I didn't have any x dependence, I could Fourier transform my problem, and it would be great, very, very simple. I just use Fourier inversion. Now, in real life, you do have x dependence, and you cannot do this. This makes zero sense. But nonetheless, there's a machinery that deals with this. And in that machinery, what you do is you replace the derivatives by the corresponding dual variables. So you do what sort of seems to make sense, but actually doesn't. But anyway, works if you do it right. All right. So the object is that you get a matrix that varies from point, so that's x, to point. That's another x. And momentum, that's psi, to other momentum psi. So it depends both on x and on psi. Okay. Now, the other thing is that this matrix is not scalar. So in the sense that it's not a multiple of the identity matrix or identity map. But nonetheless, it can be diagonalized. And the eigenvalues, when you diagonalize, are the speeds of the various elastic waves. Now, the nicest situation in elasticity is isotropic elasticity, in which case there are two kinds of waves. So I apologize to all the earth scientists who, for whom all this is going to be really boring. And but anyway, so there are two kinds of waves: the P waves and the S waves. And what they correspond to is the P waves correspond to a simple eigenvalue, so multiplicity 1. The eigenspace is one-dimensional. And the S waves to in 3 dimensions anyway, to multiplicity 2 eigenvalue. So the pressure and shear, so the polarization of the wave is different. In anisotropic elasticity, what happens is this S wave eigenspace is broken up, at least in most parts of phase space. So really remember that this matrix depends on x and psi, so the eigenspaces depend on x and psi. Typically, if you have a random matrix, which of course this is not, but if you had a random matrix, you would expect one-dimensional eigenspaces. This is not true in isotropic elasticity, but in anisotropic elasticity, for most x and psi, this is what's going to happen. Okay, so so this is quite complicated, but there's a subset of these anisotropic problems called transversally isotropic, in which there's still a preferred axis. In which there is a preferred axis, with respect to which, so this is say the axis, with respect to which this matrix is rotationally symmetric. So, so remember this G0 is a Euclidean metric for us, if you want. But I mean, it's not. It's even if it's a Euclidean metric, it's nicer to state things geometrically. Okay, and so what happens in this case is that that there will be three kinds of waves. So there are modified p waves. So this is these QP waves that I mentioned earlier, and this and there are these broken up S waves because the eigenspace breaks up. So this is QSV and QSH waves, and they correspond to different polarizations. And these QSH waves are the ones that very much behave like isotropic elasticity, in the sense that in fact they are given by a metric function of a Riemannian metric. So they're going to be given by a quadratic polynomial. So I'm going to have a formula for this in just a moment, while these QP and QSV waves have very different characters. So the upshot is, in isotropic elasticity, you had two different kinds of waves, and in fact they both behaved very much like the Riemannian geometry problem, although I didn't state this explicitly. In the anisotropic setting, there are three different kinds of waves because the multiplicity of two breaks up. But one of them still behaves just like you would love it too, because you have a nice geometric result. Okay, so so a bit more about this transversal isotropic stuff. So in this case, there are 5 material parameters. So one way of numbering them is this A11, A13, A33, A55, and A66. And so these are functions of the underlying position space, so the x variables. And then there's an extra thing, which is because you're thinking of this as a problem in which is geometric problems. You have this axis of isotropy, but it can vary from point to point. So you can encode this direction by a vector field, or I actually more like the dual objects more, so by a one form. In any case, the same sort of thing. And so in this case, the energy function, so the Hamiltonian, right? So this is classical mechanics. Everything comes from Hamiltonians. So the energy function, that's like the metric function, the squared length of a vector, that only depends on certain of these material parameters, namely A55, A66, and the direction of the axis, which I'm encoding in omega. Okay, so then if you, at one point, your favorite point, you can always choose your coordinate so that the orthogonal coordinates and the third coordinate is aligned with the axis. And at that point, then, this energy function, so which is going to give the geodesics, you can just write down very explicitly in terms of this A55 and A66. This would correspond to the principal symbol of this differential operator, giving us the linearized elasticity. And the isotropic case is when these two parameters, A55 and A66, are the same. I mean, it can still vary with x, but they agree with each other. And so in this case, this is just a multiple of G0, so the Euclidean metric. So this is a special case in which the metric is conformal to the Euclidean metric. Okay, so that's isotropic elasticity. In general, in non-isotropic elasticity, in transversal isotropic elasticity, it's not a multiple of the Euclidean metric, but just another metric. Okay? All right. And so it's another metric. You can just write down what it is. And it turns out that a nice way of thinking about this, as sort of invariantly, is that you have a metric that's a multiple of the Euclidean metric plus some other multiple of this one form given the direction tensor with itself. Okay. And one thing that's useful to keep in mind is that so this one form, right? It's a linear functional on vectors. Its null space, its kernel is well defined as the two-dimensional subspace of the tangent space on which the metric is just a constant multiple of the background Euclidean metric. So you have this one form, that's a vector if you want, and so it has this two-dimensional null space corresponding to it, and so that's well defined. Okay, so as I record, under some assumptions, which I'm mostly ignoring for the purposes of this talk, you can recover a Riemannian metric. So I said the global version, but for example, you can even do it locally. That sort of indicated that this layer stripping part. You can recover a Riemannian metric from its boundary distance function. So travel times the waves between boundary points. So what this tells us, because this is a Riemannian metric, this is the metric function of a dual the length function the length of covectors correspond to a Riemannian metric. What this tells us directly, no work, is that in fact from this quasi-SH travel times, we can recover this metric as we wrote it in this abstract form, G is alpha G0 plus beta minus alpha omega tensor omega. We can recover it up to the diffeomorphism, up to potential diffeomorphism. And then the question is that whether this is actually present in the problem, this coordinate change freedom. So in fact, what we show that it's not present under an additional condition, right? So I mean, here the metric has a special form. Any other metric that's given by the pullback by diffeomorphism, so change of variables, will have the same distance function, but chances are it won't have the same form. So the question is there anything of the same form that gives you the same distance function? And so the answer is that under an additional condition, there isn't. Okay, and what's this additional condition? So this is very nice geometry. So I never thought that this would actually come up into in an actual very concrete kind of inverse problem. So an important property of a one form, so family of covectors, is its integrability, or rather the integrability of its null space. So it varies in some crazy ways. In general, it's completely crazy. But you can ask whether this two-dimensional hyperplane distribution, or plane distribution in this case, is really the tangent space of some smooth family of submanifolds, which are just then level sets of some function f. And so then omega is a multiple of df. And if so, then of course G has this form. All I did is substitute df and change the constant in front. And in geological terms, this would correspond to a layered material where the layers are given by level sets of f. So what we are assuming is that this in principle, I can pick in a smooth but crazy way the direction of the isotropy axis from point to point. And if I do that, then I can't solve my problem. But if I make a very natural assumption that in fact it's integrable, so it corresponds to somehow layers, but layers that keep undulating, then in fact I can. And so the result is that again so this is with Martin de Hoop and Gunther Ullmann. And so under this integrability hypothesis, together with some non-degeneracy statement, this function f, so whose level sets are the normals to this level set give you the isotropy axis, as well as as I relabeled this, so alpha and beta was the earlier thing, right? So alpha and beta are the reinterpreted material parameters, so they're like A66 inverse and whatnot. Anyway, so basically the upshot is that the isotropy axis together with A55 and A66 can be recovered from this quasi-SH travel times. Again, there are the assumptions that I'm suppressing a bit. And so the upshot is that because of the form that we are requiring to get this transverse anisotropy, there's no coordinate change freedom. So you can really recover all these two parameters together with the variable axis. And this is just from the SH travel times, which, to tell you the truth, are probably possibly the worst travel times, but I don't in concrete measurements, but I don't know. The intuition. All right. So. Okay, so ideally what we would like to do now is to recover everything else. So A1, what's left is A11, A13, and A33. But I mean, it's completely impossible from these QSH waves just because they do not enter into their wave speeds. Okay, and so now is the messy-looking formula. So the messy-looking formula is what the wave speed, so it's actually twice the Hamiltonians, for the other waves are. So there's a plus minus square root. So one of them is the QP, other one is the QSV. And there's a new parameter I introduced, which is this E squared. That's just basically replacing A13 if you want. And in isotropic elasticity, what will happen is that A11 and A33 would be lambda plus 2 mu in terms of the lambda parameters. A55 would be mu, and E would be 0. And then if you just compute this, that gives you exactly the usual isotropic wave speed, which again would be given by a quadratic, a nice quadratic polynomial. And again, you would be in the world of Riemannian geometry. Everything is nice and quadratic. Okay, so and then in general, it's a change of variables to go to another system. But when E is not 0, then this is not a quad. So if E is 0, then you can just you have a square rooted, so you get rid of it. But when E is non-zero, you cannot just do that. And so the wave speeds are not given by a quadratic function. And so it's not a Riemannian or elliptic in this ellipsoidal sense problem. So in particular, the Riemannian result is not applicable. So that's sad, because the Riemannian, I mean, really the proof of the previous theorem is about a page, given the Riemannian result. So that's really neat. But now it's not applicable. But the important thing is that the analysis of that paper is, I mean, of the Riemann boundary rigidity paper, is based on studying a class of transforms which are behaving like microlocus, so in phase space, weighted X-ray transforms along curves. And even this generalized, so with this crazy-looking square root, I mean, this looks like a mess, but it doesn't matter. It's a special case of this class of transforms that Gunther and I started considering. So the techniques are still applicable. I mean, the technique is applicable, meaning that you start doing things with these techniques and you get a result, as I'll explain in a moment. This result might not be what you really like, but you know, that's what it is. That's how things are. So you have a way of dealing with this. Sometimes you hit difficulties, and then you know what you have to address. And that's what Joey mentioned and in his quick talk, and that's what he's working on. All right. So to summarize things, there is 3 quantities, A11, A33, and E. And we have 2 different wave speeds, this SV and the P quasi those waves. And so one way of stating a result. Okay, suppose you already have the SH, the QSH stuff. So you know the axis, you know the A55 and the A66. So you have the 3 other things that you want. And the theorem is that given 2 of them, so this doesn't look very good, because how would you know the other 2? Anyway, it's a partial result. Given the 2 of them, E squared and A33, the third one, A11, can be recovered. By the way, in the elastic, the isotropic case, right, E squared would be 0 and A33 would be A11. So in that case, this would look pretty vacuous, but in fact that would give you A11 directly. In any case, the Riemannian result is applicable. All right, so it's not so good, but you can do it in a slightly different way. So what seems more reasonable is to say that A33 and E squared are functions of A11. A33 might as well assume that it's an increasing function of A11. In the isotropic case, remember that A33 was actually A11, and E squared was 0. So for perturbations of the if you want a big family of perturbations, the isotropic case, this would be true. And so the upshot is then you can recover A11 from the remaining wave speeds, and hence everything else. Okay, so that's what we can do right now. So there are some successes and some limitations. So I'm going to recall the background for this to explain why we can do things, why we can't do other things, and what we can do, what we will need to do the other things. Okay. So the basic thing is so I'm going to follow the path that Gunther and I started some years ago. And what you do in these sort of problems very often is to consider some sort of normal operator. So let me say this very quickly. So this was I stated this very nonlinear problem. So the very nonlinear problem is given, say, a metric or material parameters and axes or whatever. You have so from those you get travel times, and this is the problem you're trying to invert. Get back from travel times to these data. So it's a very nonlinear problem. Now, a linearization of this very nonlinear problem is, roughly speaking, an X-ray transform along geodesics. Okay, and so that is to say, you integrate functions like maybe it's going to be some of these material parameters, components of the metric tensor, something like that, along well, geodesics or the whatever curves these elastic waves travel along, whatever you want to call them. Okay, so and so if you have a transform like this, like an X-ray transform, one way of getting at it is to compose it with its adjoint. So you have a transform I. Well, then take I star I. So that brings back to the domain you started from. Okay, and so this is what's called a normal operator. All right, and then and so this plays a key role in what we do. More precisely, what we play a role is that you put an actual localizer in between. So it's going to look like first I, then there's some sort of phase space cutoff, chi, and then it's going to be an I star. Okay, so let me just show you a picture. So this picture, so this M is the domain. So this was the ball or the disk really in the earlier picture, but you're supposed to think it's at least three-dimensional. Okay, so this ball, that's M. So that's this, it looks like a parabola here. Anyway, that's the ball. M tilde is just sitting in the Euclidean space if you want. And then what we do, right, we had this functions whose level sets were convex or concave, whichever you're looking at it. And so what I'm going to do is I'm going to cut off my problem at one of these level sets. So I'm just thinking about a spherical cap, so it looks like this lens. That's all I'm thinking about. And so I had the original boundary of this domain, so like the surface of the Earth. Now that actually turns out to be almost irrelevant. So what it does, it gives you data, so that's nice. Another thing it does in terms of analysis, it constrains what you are trying to recover. So you know everything outside it. It's the empty space, so you don't care. Okay, so you extend in your favorite way. What's actually really key in terms of analysis is this new boundary you introduced. So it's an artificial boundary. It's not there in real life, but you're going to stop there. You're trying to only figure out what's above it, what's up to it. And in terms of analysis, this is what actually plays a key role. And what happens is that this I star I kind of operator, or the I star chi I kind of operator, is going to be a pseudo-differential operator, which those of you working on imaging would know very well. But this piece of the boundary, so it looks like a nice finite piece of the boundary, no big deal about it. What it really does analytically, it gets pushed out to infinity. Okay, so what this is, one way to think about it, is what it is if you have Euclidean space. Well, Euclidean space is very big. There's this big infinity out there. And it's very tempting. You postpone all your difficulties to infinity. That doesn't work. You have to face your difficulties sooner or later. One way of forcing yourself to face your difficulties is to compactify your problem. So make Euclidean space into a closed ball. Okay, now you have a sphere at infinity corresponding to going to infinity in different directions. So this artificial boundary behaves like a piece of that sphere at infinity. Okay, and so the analysis here is behaving like going to infinity in different directions in Euclidean space. But all your favorite Euclidean space techniques are going to be applicable. So that's this apparently Shubin and then geometrized by Marrow's pseudo-differential operators. Okay, and then so let me quickly finish by saying what goes well and what goes wrong. So what happens in this case is that your operators, so this is going to be, I admit, slightly specialized. So it's more like for people familiar with imaging and various other things like that. So it's pseudo-differential operators. So they have symbols depending on position and the dual variable. So x and psi, I called it earlier. I'm calling it z and zeta just because now it's supposed to be Euclidean. So it's because I'm going out to infinity potentially. Okay, and then the point is that there's this machinery, this pseudo-differential operator machinery that lets you, for example, invert such operators under an extra condition. Like 0 you cannot invert, right? I mean, no matter what. There's no magic for inverting 0. But as long as you say that in the appropriate sense, your operator is very far from being 0, and that's called ellipticity, you can. So you have upper bounds for symbols. That's just a definition of being a symbol, and ellipticity is a statement that there are lower bounds, comparable lower bounds. And then the real theorem that proves these non-SH results is that these modified, localized, blah, blah, normal operators that arise here in this linearization, that's the Stefanov-Woolman formula, are of this kind that I just described, this asymptotic Euclidean problems. And moreover, this symbol that I described, this AZ zeta, is not fully elliptic necessarily. So it's fully elliptic when, as z goes to infinity, the position goes to infinity, the momentum stays bounded. But not necessarily as momentum goes to infinity. But however, for the A11, from the QP travel data, it is. So for A11, this is why we could get the result. For A11, we have a problem that's well behaved in every possible sense. But for the others, no, there's a degeneracy. So sometimes things are 0, and you're trying to divide by 0 if you're trying to invert. In some places in phase space, not a lot, but some places. And you can actually analyze precisely how this happens. And the statement is that this vanishing is always in a non-degenerate quadratic way. So things can be 0, but it's like, say you vanish at, I don't know, y equals 0, then it will be looking like a constant times y squared, where this constant is non-zero. Everything is non-negative, so it's a positive constant. OK, and so I think this is going to be the end. So, OK, so let me explain what happens and precisely how this fits into this QP, et cetera stuff. So what happens is that you can, in fact, compute this principal symbol, this leading term of this I star I or I star K, whatever. And what it is it's sort of a, so what you have to do is you're given a point and given a direction, or a co-direction, really, the momentum, frequency, if you want. And what you have to do to compute things there is you are going to take a certain weight, a weighted average of certain quantities along vectors that are annihilated by this. So orthogonal, if you want to think in geometric terms, but I mean it's really duality, so it's really annihilated. And the special thing, the special direction, is really the axis direction. So so the direction was df. Remember, f was the function whose level sets gave you the layers. Okay, so if you do that, then unfortunately, in the orthogonal directions corresponding to it, so this is the level set directions, if you just stare at the formula for the wave speeds, here they were, A33, so you already know A55, so that's not an issue. But A33 and E only enter with this psi3 tilde squared factor. And that's, these orthogonal directions exactly where this thing is vanishing. Now, if you average 0, you get 0, so there's no half with that. So the point is that the way this leading order term computation works, A11 enters into it in a very nice non-degenerate way. I mean, like really non-zero kind of way, elliptic way, while A33 and A13 enter in a way that in some directions become degenerate. Okay, and then what to do about this? I think Joey mentioned this very quickly. So because the quadratic vanishing, this is called something like double characteristics, and these were studied in a classical paper of Guillemin and Ullmann. But you have to extend everything to this more general situation where there's artificial boundary, where this artificial boundary is really an infinity in Euclidean space. And so that's the project Joey's working on. So I believe things should work, and which the statement would be that everything is determined from the, like all the material parameters are determined from all the wave speeds. But of course, this actually has to be done. So we'll see what happens.